Oh, sorry. Can you, thank you. Good morning. Um, Thank you very much for coming. Today we're going to talk about Bayesian machine learning, and in particular we're going to do this using a software called Edward. I know originally I had put PyMC3 on the tutorial abstract, but realizing that there's another one, was a very similar talk talking about PyMC3, I thought let's concentrate on Edward and make this less redundant. But you're going to learn something very new today. So a little bit about me. My name is Torsten. I'm a data scientist and data engineer, software engineer. In my previous life, I was a physicist, a theoretical physicist, and I work at a company called Unada. And today I'm joined by two co-workers, by Diego and by Sen. Maybe you want to say something a little bit.
Sure. Thank you, Torsten.
It's not on.
I can speak without the mic. So, thanks everyone for joining us. A little bit of a mandatory, shameless self-promotion about Unada. We're building the grocery shopping experience for the future. We're a one-stop shop for grocery stores to manage the entire digital experience for the customer. That includes e-commerce. Thank you. That includes e-commerce, digital flyers, the in-store experience, and some other things. We use Python. It represents north of 90% of our stack, so we use it all over for our APIs, to talk to our databases, to manage the asynchronous computations that we do, and also for data science. So thank you for being here.
Thank you for coming. At the beginning, I was asked to make a few announcements. So PyCon has asked me to tell you about the survey that we have. So for this particular tutorial, there is a survey, and you can go to this web address after the tutorial, please, and fill it out. There will be a break, 10:15. I will make an effort to think of it. If not, please raise a hand and say, hey, I want a break. And there will be coffee and tea and all of that served outside of this room. Lunch will be at 12:20, so directly after this tutorial in the Oregon Ballroom. It's just the way up and to the left. And if you have requested a kosher meal or any special meal, please let the server know. And well, I see everybody bought laptops, which is good. So if you need power, there should be power outlets on all the tables. Be mindful of sharing them with others. And that's it. I can skip this. So today, the outline will be first the introduction. The introduction will actually be quite long, and I'll mostly will be talking. So that gives you also additional time to get the setup right. So if anybody has still problems installing software or importing packages or any of that kind, there are two helpers here, and we also have a solution if you cannot get it running. So I have this hosted option here. That should obviously be only one HTTP, sorry about that. So if you go to this web address and you have to add the port 5000, which is not in this slide, unfortunately, then you can use also this.
Just a couple things about the hosted setup. Please only use it if you weren't able to get set up locally. If you think you're close to getting your setup locally, then talk to us through the chat channel or raise your hand and we'll come help you out. Leave the hosted setup for really the people that are struggling and won't be able to get up and running locally. The reason for that is it's a shared VM. It's pretty large, but it's still a shared VM, so performance won't be as good. So that's point number one. And point number two about the hosted setup is try not to hit run all on the notebook as soon as you load up the hosted setup. That's because there's a ton of cells in the notebook, and some of them are a little bit more intense than others. The other thing about the hosted setup, if you know your Python and you know your IPython, you know you can run arbitrary codes and arbitrary commands, so you will bring it down if you want to. So just be mindful of the fact that this is for everybody to share on. So that's it. Just be careful how you use it. Thank you.
All right, back to the outline. So as I said in the beginning, there will be plenty of introduction, introducing you to Bayesian statistics and how this all works. And then after that, we will look into a little toy example, if you will, the coin flip. And we look at it in a Bayesian way. After that, we will look at a little bit more applied stuff. So we're looking at A/B testing. After that, a little bit about curve fitting and how you can do this in a Bayesian way. And after fitting curves, we will look at fitting categorical data. So this is a classification problem. We also address it in a Bayesian way. And at the very end, if there's time left, we're going to have a Bayesian take on the so-called Netflix problem, which is just their recommendation problem, or used to be until they changed their recommendations to just thumbs up and thumbs down. So let's get started. So all this is about making decisions, making rational decisions when you're faced with uncertainty. And if you're lucky, you're not faced with uncertainty all the time. So you're looking at situations where you have to make a decision, where you have to look into possibilities where the outcome is uncertain. And usually when you are faced with such a decision, you make mistakes. So your decisions tend to be impulsive, or you just look back to your personal experience and you try to come up with a solution there. And these strategies solving these problems tend to be risky. So this all shows you just that we're very terrible decision makers when it comes to making decisions under uncertainty. And what is true for us as people is certainly also true for companies. So if you think about an executive who has to make a decision about something that is very critical to the business, and there is an uncertainty involved there, the executive would like to have some tools that help to solve these issues, these uncertain problems, using data that they have. So companies usually have a lot of data, and they want to leverage this data to make better business decisions. And probabilistic programming is a tool that can assist this process, this decision-making process. So it helps you to utilize the data that you have to make more rational decisions. And what is probabilistic programming? So, well, one way to say it is like it's just a tool that allows you to make rational decisions under uncertainty. But more concretely, it's a way to encode your beliefs about the particular set of data or the situation that you're facing. And if you look at the data, you can encode how you think this data might have come about, how it could have been generated. And encoding means actually use code. So it's basically a programming paradigm, a programming language, if you will, and you encode your beliefs in code. And then if you want to make a decision, what you do is you use probabilistic programming to solve the so-called inference problem. So and this just means that you update your initial beliefs that you stated in terms of code, given the new evidence that you have, given the data that you got. And probabilistic programming then also allows you to iterate over these assumptions that you make, these initial assumptions that you baked into the code, by looking at what inference provides you, and then going back and making changes if this doesn't solve or address the problem sufficiently. And the probabilistic programming system that we're going to discuss and study and work with today in this tutorial is Edward. And Edward is developed by a team of researchers at Columbia University, the first and foremost by Dustin Tran, who has published many papers already on Edward and about probabilistic programming in general. And Edward was designed to support probabilistic reasoning and inference at scale. So that means for large data sets and potentially involving situation where the very complicated situations that allow that involve a lot of thinking and modeling. And in order to do that, Edward uses techniques that are coming from the deep learning community. So it actually is based on TensorFlow, and that's why I all had you install TensorFlow there. And how TensorFlow helps here, we will look into later. But what Edward does, it provides you with a language, probabilistic programming language, that in essence declare let you declare parameterized models. So basically little stories about how you can simulate the data that you observed or data that's very similar. And then also Edward has baked in scalable inference algorithms. And these algorithms are used then to figure out which model parameters, so which which cranks you can turn in your model, in your story, in your description of the situation that yield simulated data simulations that are consistent with your observations. And this is exactly what you need when you want to make rational decisions. You want to know these possible parameter values that are consistent with your observations, with your data. So let's look at the simple example, which is a coin toss. And so someone has given you a coin, and you want to make an experiment where you toss the coin 100 times just to find out, well, how fair this coin is when you toss it. And then you observe this data. So you can see here there are 100 coin tosses. Zeros are tails, ones are heads. And then you can count how many tails I have, how many heads I have, and you do that here, and you see, okay, there are 57 tails and 43 heads. And you can ask now, oh, is this a fair coin? Shouldn't have a fair coin generated exactly 50 heads and 50 tails if you toss it 100 times? We don't know. So the answer is actually could be, but also could be an unfair coin, because these results, 57, 43, they could have just occurred by chance, even for a fair coin. This just shows you that the intuition that we have about uncertainty and probability in these settings that deal with uncertainty, they're difficult to manage, and we're usually bad at this. And that's where software can help. So in Edward, you get help by basically following 3 steps. So if you want to ask what can we say about the fairness of the coin, the first step is you posit a so-called generative model. So that is, you start with a simple story that tells you about how this data that you got could have been generated. And so in other words, how could things be arranged? How could the universe be that you end up seeing these coin tosses, like before in the previous slide? And so basically, you start with assumptions about how coin tosses work. So let's say you start with a fairness, and then given a particular fairness of a coin, you define a process by which then coin tosses come about. So basically, you start with a fairness, and then you go to the coin tosses, so that you basically work in forward direction. And inference is then the backward direction, so you have the data, your coin tosses, and you want to go back and study what was the fairness that led to these observations. So here, in particular, you want to infer the fairness of the coin, but in general, it's just you infer the specifics of that particular story, this particular model that you defined. And the last step is criticism. So you criticize all these steps that you went through now, the first and the second step. So can this simple story that you made up there, and you're going to start with a very simple story because you have to start somewhere. Can this simple story already explain these observations you had? And if it can't, which is usually the case, you iterate. You go back and you make changes to step 1, to your model, your story, make it more complicated maybe, or change other assumptions. And then you go through these steps again. So basically you're operating in a loop. And Edward is designed around this particular loop. So you go these 3 steps many times, potentially. So let's look at the first step, model building. So model building is just a process of stating your beliefs about how data could have been generated, as I said before. And these models are very simple. They're simplified descriptions of the world. And that means they're also valid in very particular situations, so in a particular certain regime. They break down in others. And statisticians declare these models in terms of mathematics. So they come up with abstract mathematical descriptions. But completely analogous, complete equivalent to that is actually a description in code. And this is where Edward comes in. So instead of looking at math, you can also look at code that defines these stories or models. And then what a model is actually about is it allows for the simulation of data. So this is this forward direction that I mentioned forward. So you start with some initial guess of what, let's say, the fairness of the coin is, and some belief of how the coin tosses work fundamentally, and you can then simulate the data. And I included also here this quote from George Box, a very famous statistician, a mathematician, who said, essentially all models are wrong, but some are useful. That means just that you make very simple assumptions about the world, but even with these simple assumptions, you can come to useful answers. So let's look at the more mathematical description of what these models are. And then I'm going to switch to code. So if the mathematical object that we work here with is the so-called probability distribution. And the symbol for that is usually P or PR. I chose P here now, P for probability. And these probability distributions have parameters. And the one is, in this case, the fairness of the coin, which the thing that we don't know. And the data goes also into this equation here. And in this case, for the coin toss, these are just the observations, like the number of heads and tails. And what are now these objects here? So on the right-hand side, the first one here, this one is so-called the prior probability. So what this means is, or what you encode in this object is your initial belief of the possible values of this fairness. So that means, for instance, if you got this coin from the mint, and then you probably think that this coin is quite fair. Like if you throw it 100 times, you probably think it should be heads and tails more or less 50-50. But if you get this coin at a trick shop or something, or if you suspect that somebody wants to trick you with this coin, then maybe you want to encode into this thing that you think this thing will be very biased. So maybe it only will show you heads. Or maybe it only has heads, so that both sides are heads. I don't know. But you want to encode this into this prior probability. And this other object here is the so-called conditional probability, or also likelihood. And that is encoding how, if you know the coin fairness here on the right-hand side, how this data could have been generated given this fairness. So it tells you about the likelihood of each particular draw, or each particular realization of the data given a certain fairness of the coin. And on the left-hand side, and this is a real equation here, you have this so-called joint probability. And this states the probability that both the data is observed and the coin has a certain fairness. And this actually is the recipe of how you simulate this. So you first draw from this thing. This gives you the fairness of the coin. And then you use this to draw the observations given the fairness of the coin, and you end up with this object here, if you do this many, many times. And now let's look at Edward, how Edward would declare the same story, but mathematically, but in terms of code. So in the probabilistic programming language Edward, you would have more or less these two lines. I mean, minus certain imports and setup. But this is the gist of it. So the prior probability, the fairness of the coin, the assumptions about the fairness of the coin are encoded here. And in this simple example, I just choose this probability distribution, which is a uniform distribution. That means, in this case, I expressed a prior belief that states, I don't know anything about this coin. It could be very fair, it could be very unfair. I don't want to make any prior assumption of what the fairness should be. So I give every possible value of the fairness, which is always between 0 and 1, the same probability a priori. So uniform stands for complete uncertainty about what this fairness could have been. And this gives you the prior, so this is this object here. And then you plug this in, you see you assign this to this variable, p heads, and then you plug this into this other thing, which is called Bernoulli. And Bernoulli is a probability distribution that just models coin tosses. So it's really, really simple. So like basically it says, if you give it a fairness or a probability of, let's say, heads and tails, I'm just drawing samples from that. And it will output either zeros or ones. And you assign this thing to another variable c for coin. So, and I say also here that I want to have 100 coin tosses. And there's a little subtlety here. So at this point, actually nothing happens. So since Edward is based on TensorFlow, it works with these computational graphs. And what you specify here is actually a graphical model or graphical model representation of this process of the coin toss. And this also means that if you not run this thing, if you don't request draws here, nothing will happen. So it's just a definition at this point. In order to work with it, in order to simulate now, so to do this forward step, you have to run it, as I said. So session here stands for TensorFlow session, and you can get this object. And then if you call the run method on that, and you provide it with, I took here a list of p heads and c, you're drawing samples from this joint probability here. So that means you simulate it. So what will happen is first, Edward will notice, oh, we don't have a value of p heads, so we have to draw one. So some fairness will come out of this. In this case, it was 0.49 something, so fairly fair. And then once it has that, it will then draw from this Bernoulli distribution 100 times, and you will get this array, the same, or some array like the one I showed you earlier. And then you can count how many tails and heads did I have. In this case, it was 48 tails and 52 heads. So this is how you do forward, the forward direction of this study. And let me demonstrate that. So this is the time where we want to switch to the notebook. And then I have it up here. So if there are any questions now about getting this to run, or if there are any problems, this would be a good time to raise them, because we're going to go do stuff with Edward now. Okay. Okay, let's execute the first cell. The first cell is just import. So if you have never worked with IPython notebook before, and I hope everybody has here, but basically what it is, it allows you to run Python in a nice browser interface. And you have these cells. So each cell is here light gray shaded. And if you press Shift Enter, or if you press the play button here, you execute this particular, all instructions, all statements in this cell. So let's do this here. I already did it. So what we're importing here are some things from future. Never mind. Then we're importing Edward. We're importing Matplotlib because we're going to do some plotting. And we import Seaborn, which is also a plotting package, but it's specifically designed to address working with probability distributions. We're going to use NumPy 6 and also TensorFlow. And here we get this session object. So this was the thing that I used to actually run our little simulation here. As you can see here, this is the thing I called. And I pull it out of Edward. So Edward actually defines it somewhere internally. And I can access this like this now, because I have assigned it to the variable sesh for session. And here's the color scheme that we're going to use. So I took a suggestion from Seaborn. If anybody has problems telling these colors apart, I hope not, because this one is actually designed for color blindness. But yeah, these are the 6 different colors we're going to use. And then the next cell is initializing a random seed for Edward. So we're working with randomness. We're drawing random samples. And the initial seed just makes sure that there is some initial state from where we can draw this, and this state is deterministic. One thing or two things about this. The first one is you can only do that once. So actually I could execute it again and it won't change the result. The problem is later when we actually run Edward stuff and when we use session.run, if you try to run this again, it will complain. So you can only do this once before using Edward, not afterwards. If you need to reset this to 42 for any reason, you better kill the kernel and rerun these parts of the notebook. Another thing is, although in the beginning everybody of you, and also including me, will see the same things on the screen, so everything will evolve the same way for everybody, because we're all starting with MCMC 4.2. Later you will notice that you're going to see different things than I'm seeing, and other people will see also different things. This is just because maybe you run things in different orders, or you run things twice, and that means this will just diverge and you will see different things. So never mind if you're not seeing exactly what I'm seeing. This is just because it's random. And the next cell is just for video. So there is later a cell where I'm generating a video, and this is just to make this happen. So never mind this. So let's look at the coin finally. So we're going to use some models, some probabilistic distributions, and importing them here. So you already heard about this Bernoulli thing. And you already heard about uniform, and never mind these two, we're going to discuss this. Now I'm saying I want to have 100 coin tosses, and then I have 3 functions here, and therefore building 3 different data sets. In the first case, I'm saying that my fairness is 1/2. This is an exactly fair coin. And in the second one, I'm saying this is a very unfair coin. And the third one I'm saying is, hey, just give me a random fairness. And let's just define all the 3 of those. And now let's skip this one here, but let's execute this one here. And what will happen now is Edward will, excuse me, Edward will Edward will run these instructions, and it will generate a fairness, which is 0.49, and it will create this data set here. So this is a completely, basically a toy data set. So we didn't really like do it by hand now, but we simulated our data set that we're going to work with. And in this case, I see 48 tails and 52 heads. Could you all run this? Cool. You got different numbers, okay. Yeah, if you run it, you're gonna see this plot. So what it shows is the uniform distribution. And I said earlier, like this distribution is such that it only produces values between 0 and 1. And all these values have the same likelihood. So that means there's no probability mass here and no probability mass there. In the middle, it's all the same. So it just states this initial belief that you don't know anything about the fairness of the coin. All right. So we can now go in the forward directions. So given this definition of p heads and c, we can now simulate, and we can draw from this. So we can draw a fairness, and we can observe heads and tail counts for the data set C train. But the fairness is the parameter that we don't know. So how does this help us now? So what we actually want, we want to go in the backwards direction. So this is the forward direction. We want to go the opposite way. So we have this here. So we know how many tails and how many heads there were. And now we're going to go in the opposite direction, and we want to infer what p heads was or could have been. So what are the likely values of p heads given the observations? What possible values could p heads have had such that it would agree with my observations? And this is all about, although this is what inference is all about. So what is inference? So we covered now step 1 in this loop, if you remember. So we have our generative model now. And now the second step is do this inference, do the backwards direction. So what is inference? Inference is, so you can give the definition, inference is updating your beliefs after considering your evidence. So your initial beliefs are covered in this story that we made up now in code. And inference is now updating these initial beliefs that you had considering a data set. And the data set we're going to consider is exactly this data set here. So inference is then identifying which coin fairnesses yield simulate data that is consistent with this observed data. And again, like the observations were also not simulated, but this is just to make this easier here. So yeah, inference allows you to go in the backwards direction. So mathematically, or in a more statistical, theoretical statistical way, this would look like the following. So if you go back to the description terms from probability distributions, you are on the right-hand side now. So we have this joint probability defined. We did this now in terms of code, and we have now observations. And what we need to do now is we need to come up with this thing here on the on the left-hand side. And the process by which you do this is called conditioning. So what we're gonna want is for a fixed realization of data, so for fixed observations, we want to come up with a so-called posterior conditional distribution. This is this thing here. Of the coin fairness, that describes the coin fairness, or the possible values of the coin fairness and their likelihood, given the fixed observation of the coin tosses. And this is the thing we're interested in, this is the thing we need. And interestingly, so this posterior is very powerful. It's very general. It means any statistical question that we come up with, anything that we could ask, has to come down to some manipulation of this thing. So if you look at the mean or a variance or anything that you want to do with this, or everything is contained within this thing, in this posterior distribution. Like it contains all the information that we can get. And it also is very versatile in this sense, and it is composable. And what I mean composable is this posterior now could be the prior of a secondary analysis that we do. So let's say you have your first 100 coin tosses, and then the other day you have another coin toss from the same coin, and you do these two analyses now in succession. So, and then the posterior you get at the first day could be used as the prior at the second day. So you learn from 100 coin tosses in the beginning, and then at another time you use the posterior that you got with this analysis as the prior for the second step. And this is what I mean by composition. So how does this look in Edward? There are many different methods of doing inference in Edward. And the first one we want to look at is exact inference. So exact inference means that this object that we're gonna need, the posterior, can be derived, if necessary, by hand. So that means on a piece of paper. And this is not possible in all cases, but it's possible for the simple example of the coin toss. So in Edward, what you're gonna do is you call this function here, Edward.completeConditional, and you, as parameter, you pass in this p heads. So this was, if you remember earlier, the uniform distribution, the prior. And what Edward then will derive is the posterior distribution. So p, so the probability of the fairness of the coin given a certain set of data, but we haven't really specified the data yet, and this is what we do in the second step here. So we have to have some way of telling Edward now that the actual data that we want to look at, so the observations that we're having and under which we want to study the posterior distribution, is this particular data set here, C train. So we have to bind the posterior that is here to this particular set of observations, and this is done here. So you have to submit this, or you have to pass in this dictionary here that says, okay, the C now corresponds to this training data. And as remember, C was the definition of, it's too far back, no, here, was this Bernoulli distribution. So C defined how coins come about once you have the fairness of the coin, or coin tosses come about once you have the fairness of the coin. And I'm too far here. And then again, nothing has happened yet. So we're just defining that we want to do that. This is just a description of the program right now. What we want to do next is we actually want to run this program, so this inference algorithm. And what I've done here is I just use session.run, and I'm iterating over all parameters that this posterior has. So basically what Edward will do is it will use math, algebraic manipulation, to write down basically somewhere in memory this complete conditional, this posterior distribution. And this complete conditional, this posterior distribution will have certain parameters. And in this case, there are two of them. There's a concentration 0 and a concentration 1. And you can see they're just the numbers for this. And you can plot this if you want, which we'll do in a minute. But what I want to tell you here is that Edward is able to, just by inspection of the computational graph that we built here, what the analytical solution should be. And this is possible only in a few cases. And usually it's not. So this will only be helpful for toy examples like this coin flip. So let's look at this, how this will work with our tutorial notebook here. So one thing I have to do is now I have to tell you a bit about possible ways of defining your or declaring your initial prior assumptions about the fairness of the coin. So what I've done here is I have defined three possible choices. I mean, there are many more, but I picked these three here for the fairness of the coin. So the first one is actually one that states that the coin is extremely fair. The second one is one that states that the coin is extremely unfair. And the third one is one that states that the coin is something. You don't know what it is. And I can plot this. It looks like this. So we've already seen one curve of those, the red one. So the red one was this uniform distribution. But you noticed maybe that there was this line that I commented. So this line would have stated that the unknown, the prior distribution for the fairness of the coin, which you want to state that the fairness is completely unknown, this line is commented here, and instead I use this line here. And in fact, this beta thing here is, with these two parameters, concentration 1 and concentration 0, is completely equivalent to this one. So beta is actually a family of distributions that is parameterized, and beta can interpolate between very different things. And given these two choices for concentration 1 and concentration 0, it happens to agree exactly with this other thing here, uniform. And that's also why this red graph looks exactly like this graph here. So you see there's the value 1 here, and well, you can imagine that this is also 1. It actually is. And it's completely flat. And now the other choices are the fair coin and the unfair coin. So the fair coin is in blue. And you see this is this really narrow thing, and it's 0 almost everywhere except for this region around 1/2. And this is by design. So if concentration 1 and concentration 0 happen to be equal, if they also happen to be very large, in this case 1,000, then what you will get is a beta that is very narrowly confined about around 1/2. So with this, you say that whatever the coin fairness is, it is very close to 1/2. So this would be the case where you trust, let's say, the mint. And in this other case here, where you have this unfair coin, you get this green curve. And here what I want to express is my belief that this coin wants to trick me. And it could be that this coin is severely biased towards tails, which would sit here. So 0 means tails and heads means 1 in this spectrum here. And this means that it could be either very biased towards tails, or it could be very biased against or towards heads. And I don't know which one, so I just picked the mean out of both, basically, or like I add them up, and I get this symmetric thing here. So it's basically highly peaked around 0 and highly peaked around 1. Okay, so let's now define our generative model, our forward model, so the model that allows us to go in forward direction to simulate stuff. And I'm picking here the unknown one, so the red curve, basically. And the next step is to do this exact inference, and I put everything already here. One further thing is for the seed that I chose, the 42, the first value that I get for the fairness of the coin was something like 4.936, whatever. So usually we won't see this. So this is the unknown, but in this case, since we simulate our data set ourselves, our observation that we want to work with ourselves, we know what that is. So we can always check what we get here. In reality, of course, we don't have this luxury. But yeah, so I put this here too. So this vertical line here is actually the value for 0.49. For you, it could be indeed a different value. But in my case, actually, it agrees very well with this blue curve. Nonetheless, I chose here to use the red curve, so the red prior that is states complete. You don't know anything about the fairness of the coin, and in this case, my exact solution tells me that the parameters of this posterior will be 49 and 53. So let me just plot this. So this is the result. So the blue curve is what we started with. This was the prior, and the green curve is now the posterior that Edward derived analytically. And as you can see that this curve is more or less in agreement with what the true value of the fairness was, but the peak here doesn't really agree, and there's still some uncertainty. And this is very important here. So the answer that we get is not that, hey, this coin has this or that fairness. You get this distribution of possibilities, and the more likely they are, the higher the value of this curve. So like the model thinks that this value is probably the most likely, but it still also gives you this spectrum of other possibilities that are encoded here with their weights. So it knows now with very high accuracy that these values of the fairness are more or less impossible given this data, but there's this region here where it doesn't really know. So there's still this residual uncertainty left. Yes. Yeah, so the question was, how do you interpret the y-axis, the scaling? So the scaling is such, and this is not a mathematical aspect of it, that if you integrate over these curves, you get exactly 1. And this is just for internal consistency of all that. So if you sum up the surface area under these curves, it will turn out to be exactly 1. And this is just convention. So the value 8 doesn't mean a particular likelihood now. It just yeah. So you just fix the area on the curve, but not the y value. Yeah, go ahead. Yeah, I'm getting to that in a second. One further thing that I want to mention here is, so getting this probabilistic answer, getting this distribution instead of a point estimate, instead of a mean, instead of, I don't know, a single value for the fairness, is exactly what you need when you want to make informed rational decisions given uncertainty. Because this thing is extremely clear, extremely explicit about how much uncertainty there still is left after this analysis. And having this honesty in your answer is actually what makes you able to make these rational decisions. If you don't know what the certainty of your answer is, you cannot really reason about it and cannot come to a rational decision. So having this uncertainty encoded in your answer is really extremely powerful. And this is why, although these probabilistic distributions are a bit tricky to figure out and work with, they're extremely valuable. And this is the right way to do this. So now the question was, what do these concentration 0, concentration 1 values mean that you get here? So it turns out that the exact answer for this, so the exact posterior, is again a beta distribution. So I said this beta thing here is some sort of like family of things that can take different shapes given different parameters. And you see it is the same parameters, concentration 1 and concentration 0. So it turns out that Edward knows this, and it turns out that Edward then sees that the answer, so the posterior distribution, the thing that we're looking for, is again this beta distribution, but now with different parameters. So we started with 1, 1, which gave us this flat line, But now after doing this analysis, we're getting 49 and 53. And maybe you have seen something. Maybe you have seen that there was 48 and 52 here. And if you look again at the numbers, where were they? 49, 53. Minus 1 each is 48 and 52. So basically the answer is, hey, I'm looking at the heads, I'm looking at the tails, I'm adding them to the concentration 0 and concentration 1 value. Concentration 0 for tails, concentration 1 for heads, and I'm getting my posterior. But this is only in this very simple case. So this is just because this coin flip example is so simple. Does this answer your question? Cool. And then we can do a bit of criticism. So we can look at what our mean and variance are. So the mean would just be basically the value that sits smack in the middle of this curve here, and it turns out this is 0.51, and it's a bit off. So like the true value was 0.49, but yeah, and then this value here expresses the variance. That means the width of this curve. But again, like these are single values. Although like, I mean, if you just provided, let's say, the mean or so, then you don't know really what the width of this curve was. So like it could be really, really wide. It could be very narrow. If you then add this additional number here, 0.04, which specifies the width of the curve, then you get a bit of better feeling what the remaining uncertainty was. But this only works for very simple shapes. So if you have, let's say, 2 peaks, so like maybe there's another peak here, then the mean would fall in the middle here, but the probability mass would sit in these two narrow things. So the mean would be somewhere where there is no chance that the real value was there, and would give you the complete wrong picture of what the answer is. So use the mean and also this posterior standard deviation. STD stands for standard deviation. With a grain of salt, it could be giving you a wrong impression. So yeah, that's why I think the posterior distribution is actually the right thing to look at. Okay. What I would like you to do now is, so I don't have any real exercises, so there's no like gaps in the code and you have to fill it in or something. What I would like to do rather is I want you to experiment with it. So I gave you a lot of alternative routes here to go. So I gave you the option to use this fair data set instead of this one here, or this unfair data set. And what I would like you to do is just change the definition here, change this value, re-execute the cells that are in between, and see what the answers are, and see how this changes. And also change what the prior probability here is. You see, you could change this value here, and then you switch from the red curve to, let's say, the green one, or the blue one. Or you can even make up your own ones by, I don't know, write a new one here that has concentration, I don't know, 127 and 2, yeah? I don't know what will come out of this. Something weird. And just play with it. The only thing that you have to keep in mind here with these beta distributions, the concentration 1 and concentration 0 have to be larger than 0. If they're not larger than 0, then you will get an error. So they have to be positive. Does it sound good? Cool. so just I guess you had an unlucky draw there. Yeah. Really?
Yeah.
Maybe the.
The first time it was over here.
Did you run all the cells?
That is not that unlikely. Oh, sorry. That is not that unlikely for a fair coin, is it?
So what you should have gotten is 59 and 43. Can you go down to your answer?
Or maybe I didn't rerun these.
Maybe.
Yeah, okay, let's just run the whole thing.
All right. That's weird.
So intuitively, it's not making sense.
Can you go a little bit up?
Yeah.
A bit too far. 57, 45, but it's okay. So what were the tail and head scouts for you?
For that one that I just ran.
Yeah. So this is exactly the answer. So this is a bit of, yeah, but this shows you just like how 100 coin flips is actually not that much. It's not that much. So if you want, what you could also do is you can increase the sample size. So we have 100 points. Oh, thank you. We have 100 points. And you could also go up to 1,000 points or 10,000 points if you wanted to. And you can see what the influence of that change is. So maybe you want to spend 5 minutes also doing that. Two peaks? 2 peaks is unfortunately not possible. So it always has. Well, this thing has 2 peaks, yeah, but they're like at the.
Let's say I assume it's unfair, but I'm not going to assume that it's going to be all heads or all tails. So I want to have 2 different probability distributions.
Oh, yeah, that's tricky.
I'm assuming the beta.
Yeah, the beta has limits. I mean, they're just 2 parameters. There's not too much you can crank there. Yeah, this is not, unfortunately, how that. You cannot compose them by addition. Can you put me on? So there were several questions now regarding what if you want to express that I don't know, like you have a feeling that your coin could be either somewhat strongly biased towards tails and somewhat strongly biased towards heads. So like basically maybe you want to have 2 peaks, one here and the other one there. Unfortunately, with the beta distribution, the one thing that I told you about so far, that won't be possible, at least not with this exact inference scheme. There are probably ways to do that right now. I would say let's skip that and maybe try this at home. Well, I don't know. There's a GitHub channel, by the way. I don't know how many people are on the GitHub channel, but you can certainly also ask questions there. I won't probably get to them. Oh, there's actually things. Okay. So there were some people already in here. I didn't look at it up, but yeah. So I will look there now and then, and yeah. Also after the tutorial, actually. So if there's still questions after the tutorial, please post them there. All right. Shall we move on? Okay. So now for something different. Have a look at this piece of code here. So I said earlier, you can use a posterior as a prior in a later experiment. And this way you get this compositionality. And this is what I've done here. So let me just run this because this can take a while. Maybe you want to run it too. but what I've done here is I did exactly that. So I used the posterior as a prior. So what I've done is I splitted the 100 coin flips that we have. So if you still have like 1,000 coin flips, it would be a good time now to go back to 100, because otherwise this will take ages. I splitted this data set up into 3 parts, like 33 coin flips in each one of them, non-overlapping. So the first 33, then the second 33, the last 33. Which order I do this is actually not important, but what is important here is that I first do the inference for the first 33. I get an answer there for a posterior for the fairness of the coin after looking at this data, so the updated belief. And then with this updated belief, I go again and use it as my initial prior belief when I look at the next 33 coins. And after that, I repeat that, and I look with then another yet updated belief at the last 33 coin flips. And you can see how this is implemented here. So I have this recursive function here. It's called go. And it has 3 parameters. The first one is the prior. The second one is how many samples do I submit? And the third one are the actual samples. And it calls itself recursively. So in the body of the function, you first have the model definition. So I plug in the prior into this Bernoulli. So this is then the likelihood. Then I run inference. So I use this same inference method that we studied above. So like this exact inference method. Then I use criticism. So I just plot it. So the posterior that comes out of this. And then comes the crucial step, the recursion. I now call the function itself, but instead of putting the same prior in, I put now the posterior in that I got after the run, after this inference step here. And then the function will run again, but with this other prior. And if you do that, you see this here. So first comes blue. This is the initial prior. Then comes green, I believe. Yeah, green. Then red, and then purple. So purple is actually after seeing 99 coins. So the last coin I just forget. But as you can see, is the width of these curves. So the posterior answer, the certainty that you get after seeing more and more coin flips for the same coin gets narrower and narrower. Yeah? So like you start with this complete flat line. Already after 33 line, you get much better picture of what the possible fairness of the coin could have been. But it's still pretty spread. And then after seeing another 33 coins, so in total 66 coins, you have this red curve, which is yet a little bit narrower and moves a bit around. And this is just due to random fluctuations in these observations. And then in the last, after 99 observations, you have this final picture where you have the even narrower posterior. So with this, you can actually see the beauty and the power and the compositionality of this Bayesian approach. You can also think of this in terms of online learning. I don't know if you've heard this term, but like you can learn as stuff comes in. If you observe the world and get more information, you got more observation from it, you can update your beliefs immediately. All right, let's go back to the slides. Yeah. There should be. I'm not sure if I can do it quickly now. Yeah, I'm using Seaborn here. Oh no, this is plain MATLAB. Yeah, it should be possible. Yeah. All right. So I set this method of exact inference, like where you let Edward do the work and do what you would have to do on paper, and recognizing that the posterior is again the beta. These kinds of things that are only possible for very simple models. For this coin flip model, in general, you will have a hard time using them. Edward will just say cannot do it. And in this case, you have to approximate. So you have to do a numerical computation that gets you the answer that you need, the posterior. And why is this so difficult? Or why is this a problem usually? Well, the problem is that you cannot really solve for this posterior. So I mean, you can do it mathematically and it looks nice. So actually, if I go back a little bit, so there's this Bayes theorem, which sets them into relation. So on the on the right hand side, we have the joint probability. So this is just the numerator of this fraction here. So this is the joint probability of seeing both parameters and data. And then you actually want to have this thing that's just the posterior and this thing on the left hand side. And in order to get that, the Bayes theorem says, well, you have to divide by this thing here, which is the probability of the data, but now for these particular observations. And doing this mathematical operation here, like this thing is easy because this is just a specification of your model, of your simulation. So we have this. But getting this thing and then even also dividing through that or by this is very, very difficult in general. Extremely difficult actually. And solving for the posterior is non-trivial. Oops. So yeah, what are you left with? Well, you have to somehow do this approximately. So you have to run approximate methods. And Edward comes with a variety of approximate methods. And the first class we're going to look at later is Markov chain Monte Carlo. But before we're going to do that, I just want to tell you a bit about how you interact with these solvers, with these methods. And the story is always the same. So Edward uses an abstract class called Inference, ed.inference. And it has always, or needs always, two parameters provided. The first one is called latent var, so vars for variables. And what you do there is you pass in a dictionary, and this dictionary binds the variable that you want to infer, in this case p hat, so the fairness of the coin, to some other object. And this is, well, you can call this posterior variable. So I left this blank here because what this is actually dependent on the method. We're gonna see this later, but you have to do this. So like if you don't do this, Edward won't know what to do, or will just don't produce any results. And then you also have to tell Edward what the actual observations were. So like you want to bind now the posterior to the particular set of observation that you have, and in doing so you use this data parameter here, and you have this other dictionary where the keys are in this case C, so the coin toss model description, and the values are the extra observations. So in this case here, the training data set, the coins that we generated beforehand. So how do you run all this thing? So running means you approximate, so you do this computation now. So it's very easy. Once you have this assigned to something, in this case I called it inference, you just call .run. And you have to do this. If you don't do this, nothing happens. So this just specifies the inference problem, and .run executes it. And we're going to look at two different classes of approximations today. The first class is Markov chain Monte Carlo, and the second one is variational inference. So let's talk about Markov chain Monte Carlo quickly, because the break is coming up. So what is Markov chain Monte Carlo? So Markov chain Monte Carlo is a class of algorithms, and these algorithms are randomized, so they involve randomness themselves. And they approximate in posterior, so this is what they're made for. So the posterior, to remind you, is this thing. So the probability of seeing parameters given data and where the data is fixed to particular observation or particular observations. And what is now a Markov chain? So these are the first two words in this long term here, Markov chain Monte Carlo. So Markov chains, you can think of this, especially as programmers, as infinite streams. So given some initial value, some initial seed of the stream, you generate one element after the other, infinitely many if you want. Well, you can't get there, but like in principle. And you do so by applying repeatedly the same random function over and over again. So this random function will have a different effect every time you run it on the element. And that's why it's random. But the point here that I want to make is that this random function only cares about the last seen element in this stream. So like you get the first element, this is the initial seed, then you call this function, generates a new value, again, new value, and this is this chain that you're building up. And it's called a Markov chain because Markov is the name of a researcher who came up with this class of problems or class of descriptions where you have a memory that is only goes only one step back into the past. And you can see that here that this function you only apply it to the last element. You don't apply it to the second last element or including all previous seen elements in this stream. You only apply it to the last one. And this is this Markovian property, and this is why it's called a Markov chain, just to make this clear. And how does this look like? So you start, as I said, with an arbitrary seed. You just draw a random number, basically, or you can even define it to some value if you want. And then, in effect, so if you have just an arbitrary Markov chain, so if you have just any random function that you throw at this, and you make it such that, let's say, for the coin flip example, so the parameter is the fairness, so this thing should better stay in the possible realm of values, so somewhere between 0 and 1. So if you have such a random function, then you will see something like this. So actually this flat line here is the true answer in this case, but if you start here, then a random function will just put it somewhere, and you go another step, you're there, and then you go there. So basically you do a so-called random walk. So you just like bounce around in this space of all possible parameter values. So is this thing useful? No. So this thing won't give you any answer. So you actually have to specify a very particular random function there. And in MCMC, so Markov chain Monte Carlo, and this is now where Monte Carlo comes in, the random function is such that it focuses the chain on values that, so where the posterior, so the thing you're looking after, is large. So it goes into the interesting region, so to speak, and it stays there, and explores it a bit. Maybe it goes somewhere else for a little bit, comes back though, and stays preferably in this interesting region where the posterior is large. So this is how it looks like. So if I start here, then with the right random function, I will jump there. So maybe I will stay there for a little bit, then I jump again, stay there for a little bit, jump somewhere else, and so on. But you can see, like, since I know that posterior will somewhere around this true answer, which is this flat line here, what I expect is that a good chain focuses on this region around that. And if you run this like for infinity, or very long, here I did this for like 200,000 steps, what you will see is something like this. So here's the true value, this flat line, which is in the background, and then you had, so I didn't connect the dots of the chain, but each dot basically corresponds to one sample or one element in the stream. And as you can see, since I gave them a little bit of transparency, and you can see like they're concentrated around this true value, and like there are less points the further away you go from this interesting region, from this true region that you want to look at. So, and actually there's a mathematical theorem that for these Markov chain Monte Carlo random functions, in the infinite limit, so when you actually run this for all eternity, this chain itself will become the posterior. So what that means is, if you, let's say you slice it horizontally here, like you make a horizontal slice here that has a certain width, like a short width, let's say 0.01 or so, and then you count how many of these infinitely many points are in this slice, and you do this for all possible slices, and if you then scale it by the number of, well, infinity, so the number of elements in the chain, what you will get then is a good approximation of the posterior. So this is how this method works. So the only problem is that we cannot run this infinitely long. So for an infinite chain, everything is good, and we always get the right answer. This is impractical. So in practice, we need a finite length of the stream, so we have to interrupt this at some point. So we have to say, oh, stop after 1,000 iterations. But the problem is then the answer that we get might not be good enough. So you can see, like here, this after 200 points, this is really crappy. Like it jumps around a little bit, but you cannot really expect that this thing will be as good as this here. And the question is, what is a good length of the chain? How many elements do we need? And there's some intuition about this, but there's also some mathematical results that help there. And it's a bit tricky to work with. So what I would invite you today is expect that I mean, you can develop a little bit of feeling of how long a chain should be to be good, but I don't want to like go into the details of how you select the perfect length of the chain. All right. So in Edward supports this method of approximation, and this is how this would look like in the below half of the slide. But let's talk about a little bit more about the method itself to understand what you have to define here to make this work. So this random function that you're going to choose in Markov chain Monte Carlo has 2 steps. So the first one is you make a proposal of where you want to go. And the second step is you either accept this proposal or you reject it. And the proposal proposes 2 values of, in this case, the fairness of the coin, where the posterior is higher than it is currently, so where you're currently standing. So you want to go up here, and the posterior there is now lower than it is here, so then you accept this sample. And if the opposite is the case, so if the proposal here, or the posterior at this position is smaller than it was before where went, then where it was, then there's a certain probability with which this this jump is accepted. And this probability is proportional to the ratio, so the fraction of these 2 values of the posterior. And you work with the fraction of the posterior. And you maybe remember that the problem of the posterior was that in Bayes' theorem you have this term P of data equals observations in the denominator. So if you have a fraction of two different posteriors, this cancels out because it doesn't depend on where you are on the chain. So you get around this problem, and this is why this works. So you have a lot of randomness in this function. So first, this proposal itself is random, and the second randomness comes from this second step here, where you have this acceptance probability. So how do you use this now? So you first define the length of the chain, 10,000 elements in this case. And then we have this Q heads variable. So this was this, interesting. Sorry about that. I hope this goes away. It goes away. So where was I? Yeah, so we have this Q heads variable. I hope nobody tries to hack me here. So you have this Q heads variable, and for Markov chain Monte Carlo, so for all Markov chain Monte Carlo methods, and there are several of those that we can look at, you have to set it to this empirical thing. So empirical is just a placeholder. So you need a space where you want to store your chain elements, your stream. So you basically dump it into this empirical thing, which is just a placeholder that has a certain size. So you say, okay, I want this empirical thing, and has this parameter here, which is called paraments. And you have to say that this thing can change, and you use a TensorFlow methods to do that. So you use TensorFlow.variable, which just means that this thing can now change. It's not a constant, but can change. But you have to give it some initial value. In this case, it just shows 1/2. So all the elements in this infinite long chain, or in this case, 10,000 element long chain, are initialized with the value 1/2. And this one value 1/2 is actually not used. It's just something that you put in there. And then you have to make a proposal. And, well, you have to actually tell Edward now what this proposal should be. And in this case, I chose a uniform distribution. So remember, beta 1, 1 was actually the case where this thing looks like this. So this is the uniform distribution. So I'm just throwing anything out there. So any possible value comes out with the same probability. And then you call Edward.Metropolis Hastings. So Metropolis Hastings is now a class that inherits from this abstract inference class that you saw previously. So it has at least these 2 parameters here, latent, vars, and data. And you see now this first one, latent vars, actually makes sense. So we have to tell Edward now that it should store this chain somewhere. And we do this now with this dictionary here. So we say, hey, whatever you come up with, if you iterate this chain, please store this in Q heads, which is this empirical placeholder. And then the other thing we already discussed is you have to bind the coin toss model, so the Bernoulli, to the actual observations, which was C-train. And the last step is just to run it. And this scheme will repeat itself. So for all the Metropolis Hastings, also for variation inference, you always have this structure that you have to call Edward.SomeInference class, and then you run it inference.run. So let's do that now. So if you switch back to the notebook, then the next thing conveniently is MCMC, Metropolis Hastings. And there's our model, which is just, well, it's nothing. You just say, I want to have a chain that's 10,000 elements long. You have this placeholder, and then you run inference. And there you see is the proposal density, and then there's the call to Metropolis Hastings class. You run it, you get a nice progress bar, it takes 7 seconds on this laptop, and you're done. You have 10,000 samples. So then there's this thing here, acceptance rate. So acceptance rate is how many of these proposals that you make are actually accepted. And you remember that the proposal is just any random value. So this was this year, the beta 1,1. So it's just a uniform distribution. And in this case, when you make this random proposal, completely random proposal, you just get like 1/10 or so of accepted samples. So this is not very efficient. So you go into a direction, and this direction is completely random, and then well, what you probably observe if you go into completely random direction is that it's probably not very efficient. Like you don't go anywhere where it's interesting. So that's why most of these proposals are rejected, like 85%. So this is not a very efficient method here, but it works. So this is actually the chain. So you can see there are like 1,000 points in this chain, 1,000 elements in this stream. There's the true value, which is 0.49 in my case. Again, your case might be different. And then you have this noisy line here. Yeah, so like this is just the different accepted proposals. If you reject a proposal, then this means you're staying where you are. So sometimes you see that there's no real change. It's a bit hard to see on the scale because there's so many of these points, but there are a little bit of gaps between points sometimes, like there are like these little like gaps there. And this just means that the proposal was rejected and the chain temporarily stays where it was. And let me skip this lag thing for now quickly, but just to prove you that this actually approximates the posterior. So I told you in the infinite limit, this thing, this trace plot of the chain becomes the posterior. And you do that by looking at horizontal slices through that. And you're counting how many points were there. And since we have now a finite chain, we can just do that. We can just look at, I don't know, like this bin here, this region of possible values between like 0.4 and 0.41. And we can count how many points, how many elements of the chain are in this region. And we do this for all possible bins that are non-overlapping. And there's a word for that, or method for that, and this is just a histogram. So this is called a histogram. And these red bars here that are building this tower are exactly this histogram. And where they do that? Here. So I call matplotlib.hist, comes with the histogram function. I say q p heads parameters. So parameters are now the chain elements. I evaluate them. That means this is just a shortcut for session.run. So if I call .eval, that's the same as session.run, and then in parentheses this thing here. And then I say how many of these horizontal slices do I want? I want 100 of them. Where do I want them? I want them between 0 and 1. And then normed true just means, coming back to this earlier question, hey, what's the vertical value? So if you omit normed true, you will get some vertical value which just corresponding to the counts. But we want to have it normalized, which means if you add up the volumes, not the volumes, the areas of all these bars, these vertical bars, these bin bars, you get the value 1. And you have to do that, otherwise this one corresponds to the true answer, which is plotted here 2, which is the green curve. So this is the thing we got earlier by exact posterior method, and you can see it somewhat agrees. Agrees nicely. So how about you run that, and then we have a break. Okay, see you after the break. Sorry, what? So couldn't hear you.
Will you be making your slides available?
Yes, yes, yes. That will be on the GitHub, and they will probably run in your browser, like they do now for me. Mhm. No, I just chose a value that's possible. I don't know what happens if you choose like a negative value or something that can't happen. We'll just grab. I haven't tried actually. Yeah, we have to pick one value. You could pick 0 or yeah, but you have to give it a value.
Just a quick question. Would you mind explaining what does this line do? Right here, just the Q hand.
Yeah, this is Uh, get started again. Maybe 1 more minute or so. If you could return to your laptops, that would be great. I think there's still like 10 people so missing. Maybe they come back from the washroom soon. I wait 1 minute. There will be, yeah. I will put up the slides. Maybe not today, but probably within the time of the conference. And they will be on the repository. You can either then, it will probably create a PDF, but I guess the best experience is actually if you run it in a browser. So it will be just a web page basically that you go to. All right, I guess we have to get started now. So this was the last thing we did. We looked at Metropolis Hastings, so this very simple Markov chain Monte Carlo algorithm that is also, well, it's simple, and that's why it's nice, but it's also quite stupid, and it's going oftentimes in directions that are not really helpful. That's why this acceptance rate is so low. So like 15% or so of the samples, of the proposals are accepted, the rest is just thrown away and you have to try again. So you really you're tapping in the dark, you're going somewhere, and maybe this is an improvement or maybe not, and in this case actually most of the time it's not. And so we are looking for a better algorithm actually, because this Metropolis Hastings algorithm, if you think of more complicated problem, because we also have to think about those eventually, will get first of all harder to implement, and also be much more prone to this this inefficiency that is inherent to it. And there's another problem with it, and this goes back to the quality of the samples. So I don't want to really get too much into the details here, but I already alluded to it a little bit. So you have, because you have so many rejected samples, you have these plateaus. So like you have these gaps in this plot, and what this will mean is that you're staying somewhere for some time, and then it means that these samples are correlated. So that means that that you don't get more from them. So like they're basically wasted. And another thing is if you look at this visually, what you would like to have, you would like to have, people call this a good mixing. So that means it should be as noisy as possible. And there you can still see a little bit of structure in there. And you don't want to see any structure, ideally. And a measure for this, how good the chain is this so-called lag or lags. So for those who are a bit mathematically inclined, so what is actually the autocorrelation of that. So basically I'm looking at how, depending on a parameter, which is x, how basically correlated is the chain with itself if I give it an offset. So like basically I look at the chain, or and I look at the chain again, but first of all exactly with itself, and then with an offset, and even larger offset, and so on and so forth. So increase this offset more and more. So I scan through it, and if I plot this, I get this figure here. So in the beginning, when the offset is 0, I'm looking at the correlation of the thing with itself. This is always 1. And then it goes down, and you have this noisy thingy here. And this tail here should be as small as possible. You see this little wiggling here going on, bit of jitter. It's not too bad, but it could certainly be better. We're going to use this just to get a feel of how good the convergence and the usefulness of this particular chain is. So let's look at the different algorithm now, which is called the Gibbs algorithm. So there's a different Markov chain Monte Carlo method. So the difference here is that the random function that we apply to the chain is different. So it's still the same idea. So you're still using this finite chain where each next element is coming from the previous element by applying a random function, but the random function is different in this case. And what's particularly different about this is the proposal that you make. So previously for Metropolis Hastings, you have a proposal that you have to state explicitly. So you say, I don't know, I want to draw random numbers from 0 to 1. For the Gibbs sampling, the proposal is provided by the method itself. And in this case, the proposal is coming from the so-called complete conditional. And what that is, it is the distribution of a certain parameter conditioned on the current values of all the other parameters. So if you had not only the fairness of the coin, but some other parameter of this model that you want to infer, I don't know, I can't think of anything yet, but if you had 2 parameters there that are unknown to you, then you would derive a probability distribution of one particular parameter given the current value of the other or all the other parameters that you have, and also the data. And if you make such a proposal, using this complete conditional, you can show that this proposal is always accepted because you're always going somewhat in the right direction. So this should be better because we had seen that the acceptance rate was 0.15 or something. With this, it should be actually 1 because it's always accepted. And how would you use this in Edward? So pretty similarly, except that we don't have to state the proposal distribution. You see it's missing here. You just have to say, hey, instead of Metropolis Hastings, I want to use Gibbs. And then you state, again, your latent variables. You want to tell Edward that you're inferring p heads. You want to store the chain in QP heads. You have coin flips that you're looking at, and these are the observations for the coin flips. So this is all, and then you run this, and you get a chain. So let's do that. So here's the code. It's the same again. And now it runs, and you see the acceptance rate is exactly 1, as it should be for this method, because it's always accepted. And this is the trace. And you can already see visually it's different than the previous one. There are no gaps, and the gaps are missing because the acceptance rate is 1, and it looks much more noisy. And you can put a number on how much noise there is and how much correlation is by calculating this lag, this autocorrelation with an offset. And you can see the initial value is 1 again, but then you have this noisy tail, and the noise level is smaller. So actually this chain has better quality than the previous one. And to prove that this method also works, you see here the histogram. So a histogram again are like you make slices through the chain, make slices, horizontal slices to the chain. You count how many elements are in the chain, and sorry, not in the chain, are in the slice, and then you count this by the total number of points in the chain, and you get this histogram here. You could run this now to see it for yourself. And maybe if you have a question, you could raise them too. Yeah. Yeah. Yeah, you have less samples that are useful. You have basically only 1/10 of the useful samples than you have now. So that makes it crappier, yeah. Maybe I give you 1 more minute or so. Okay, so this is Gibbs sampling. We will use it later. But before we do so, I want to look at the best, I would say, the most efficient and the let's say most secure Markov chain Monte Carlo method that Edward provides, and currently that is Hamiltonian Monte Carlo (HMC). So the truth is that Metropolis Hastings and Gibbs, they will fail in high-dimensional parameter space. So that means, like, if your coin toss fairness was not like a one-dimensional variable, so like basically a value between 0 and 1, but it would be, let's say, a vector in a high-dimensional space. So let's say not 3 dimensions, but let's say 1,000 dimensions. Well, actually, it starts getting problematic already in smaller dimensions, but let's make the point. Then Metropolis Hastings will be exceptionally bad because you remember it makes a random proposal. And the penalty for making random proposals and uninformed proposals is becoming extremely huge if you go to higher dimensions. And Gibbs also will then have problems, because even though it makes better proposals, it still won't go into the right direction most of the time. And HMC, Hamiltonian Monte Carlo, is an effort, or is a method that aims to resolve these problems. And what it does, it comes up with a better proposal, a better informed proposal, by studying the geometry of the important regions of the posterior. So you want to go to a region where the posterior is sufficiently large, where it basically has where its mass is concentrated. And HMC does that by studying how basically the posterior is shaped, what the geometry of this important set is of values. And this is then used to guide the jump proposal. I could go into the nitty-gritty details of how it actually works, but this would be too mathematical, so I'll leave it at that. If you're interested, you can certainly look this up online. There are very good articles on HMC. I will have a link for you later. But please note that this is a very advanced method, and it doesn't work all the time, but it works in more cases than metropolisatics would, or even Gibbs. Because, and I forgot to mention that, what Gibbs needs is that you have to be able to derive this complete conditional. So the complete conditional, we saw this before. What is the complete conditional? The complete conditional is mentioned here. So the complete conditional was that posterior, basically. So this is the thing that Edward needs to derive, basically, analytically, by algebraic manipulation. So you have to be able to do that by hand on a piece of paper if you had to. And most of the times, you cannot derive this complete conditional. And if you cannot do so, then Gibbs cannot be used. And Hamiltonian Monte Carlo doesn't have this restriction. So it can be applied in cases where Gibbs wouldn't be able to, we wouldn't be able to apply Gibbs. But it has one restriction that is quite important, and it only works if you want to infer continuous variables. So it doesn't work if you want to infer discrete variables. And this has to do with the fact that in order to study the geometry, it has to calculate derivatives. So it has to differentiate basically the geometry or the functions that describe the geometry. It is only possible if they are smooth functions. So discrete would mean that they have kings and steps in them, and that means that derivatives would diverge, and this is not good for the method because it wouldn't be able to work with that. So the parameters that you want to infer with HMC have to be continuous. And in our case, for the coin flip example, the parameter that you want to infer, the fairness of the coin, is continuous, so it will work. So how does it work? In Edward, we will have to say Edward.HMC. We have to tell it again latent variables and data. So we have to bind them. And then we run it, and you have to include, or you should include, certain parameters here if you run it. The first one is the step size, and the second one is the number of steps. So to understand what they do is a little bit tricky, at least based on what I told you about the method. Suffice to say that you have to tinker with those a little bit. So I picked here two values that somewhat make sense for this problem, but usually the step size, if you make a smaller step size, the proposals will be closer to where you currently are. And the number of steps also is something that has to do with the way of how HMC basically informs these proposals. So it has to actually little bit it uses the geometry basically to come up with some sort of like motion, and this motion is evaluated stepwise, and the number of steps is just how many steps you do that, you use when you do that. So just to make this complete, once more evaluate the coin flip example with the MCMC method. In this case, it's HMC. So just when we execute these, it will take a little bit longer. HMC is more powerful, but also a little bit slower. And it will take a bit. You can see the acceptance rate is quite high, which is good. This is how the trace looks like. And this is the autocorrelation, and this is the histogram. So you see that indeed this method also solves our problem. It provides us with an approximation to the posterior. It gives quite well with the analytical solution, which is the green curve. All right. Now we switch gears a bit. So we have heard a lot about Markov chain Monte Carlo now, and we will use these tools later on in certain examples that we're going to study. But yeah. Prone to local minima. So I'm not sure what exactly you mean by that, but I would say something that Gibbs is very prone to is running into issues when I said the HMC uses the geometry of this interesting region to inform proposals, and sometimes this geometry can be very complicated and can be also very sudden, can be subject to very sudden changes. They could be still smooth, but there could be like some kinks in there or some complicated geometry. And if Gibbs encounters such complicated geometry, it won't be able to penetrate into these regions, and it will just I don't know, struggle a bit, get stuck a bit, and then maybe go in a different direction afterwards, but will not be able to basically dive into this interesting region and explore it as it would be needed for getting a good posterior. So this is an issue that comes up with Gibbs all the time, and you don't have this issue if you use HMC. I don't know if this answers the question, but this is something that you have to think about if you use Gibbs. That there are many pathological problems that you can encounter that makes this method problematic. And HMC is designed to get around these problems. So technologically, I mean, they're quite similar, I would say. So Edward is a younger project than PyMC3. PyMC is. I think PyMC2 has been along for a long time. PyMC3 has come up maybe in the last 3 or 4 years, I'm not really sure. But it's based on similar technology. So whereas PyMC3 is based on Theano, Edward is based on TensorFlow. And Theano is also a framework, as TensorFlow is a framework used for deep learning. So they're quite similar conceptually. If you asked me which to favor for your daily work, I'd say currently maybe use PyMC3 or maybe even neither. There's a third package that is quite good. It's called Stan. But Stan is in Python, and we're here at PyCon. And Edward is a young project, but a very, very intriguing one because, well, it's based on TensorFlow and it has interesting ideas. And the most important thing is this thing here, variational inference, which is very, very well implemented in Edward. And this is actually the main focus of the project. So let's talk about this a bit. So what is variational inference? So it's another technique that allows you to approximate the posterior. And if you think back to that slide where I had these 3 points, 3 steps in this loop that you execute, you have the first one was you write down the model, you specify your initial beliefs. The second one, you infer the model's parameters. The third one was criticism, then you iterate or you loop. And in variational inference, you change the second step. And what you do is basically you nest this loop within itself. And you do that by doing an approximation of the approximation. So you're saying, or what you actually, in essence, what you're doing is you cast the problem of approximating the posterior as an optimization problem. And in order to do that, you say, instead of actually studying this posterior that is extremely hard to evaluate, maybe we can do something. Maybe we can look at a simpler distribution. And this is called the variational distribution. And this is called usually Q. So you have P and you have Q. And Q will be such that it can approximate the real posterior. So Q will be a probability distribution over the unknown parameters, in this case the coin toss fairness. But it also depends on other parameters, and I used the Greek letter lambda here. And these other parameters, so with these other parameters, this is actually not a single probability distribution, it's a family of probability distributions. And the question now is, well, which, the hope is that if you make this family sufficiently expressive, such that it could, if the parameters are chosen right, mimic or even fit the real posterior that you want to know, well, then you're on the right track. Then you can actually optimize those parameters such that the difference between the real posterior, the P of params and the data, given observations, is exactly the same or very close to Q, this variational model that you build. So, and this is why you have now this nested loop. So in step 2, you will then have to build a variational model that basically replaces the posterior, and then you have to use an optimization process, which is B here. So you, and I formulate this here mathematically. So what this means is like you have some measure that determines, or that gives you a quantity or quantitative answer of how close now the real posterior P and this approximation to the posterior Q really are. And since this depends on the current parameterization of this Q, what you can do is you can just minimize it. So you basically you optimize this closeness, or this Q basically over these parameters lambda, and then you get a optimal lambda star, and the hope is that this closeness is so small, ideally it's 0, basically 0 would mean that they're identical. And if this is the case, or if they're sufficiently close, then you can just use this Q now instead of the real P. And this becomes really powerful if you choose a Q that is easy to work with. So whereas you cannot really work with this posterior because it's so hard to get, you can maybe come up with a Q that is easy to work with, that you can sample from, that you can even study algebraically, analytically, and has all nice properties that you want. I don't know if there is such a thing, but you could work it out maybe. And this is why you have to also work in a loop here. So you do this many times, you make maybe changes to this parameter family Q here, and you have this continued criticism of your method. And once you've done this now, you can go back to the outer loop of this scheme and then criticize the whole approach. So also including then criticism over your prior assumptions. So yeah, we have loop in the loop. Okay, in Edward, this would look the following. So the first box here is code for defining this variational approximation, this Q function. And in this case, I'm cheating here a little bit. I know that the answer for this problem, because we know, I mean, we have solved it analytically before, is a beta distribution. So, well, and usually you don't know that. You don't know that there is a thing that that solves exactly. But let's assume we find something, and here it would be beta, and the lambdas are now these concentration parameters, concentration 1 and concentration 0. So what you have to do is you have to say, okay, my backward model, and you assign this to the variable QP heads, which was previously this empirical distribution, now it's this beta. So this is now this variational distribution. And this is actually also, I mean, that this is both QP heads just shows that Edward basically treats Markov chain Monte Carlo methods and variational inference methods basically the same. So they're all inheriting from this inference class, and they all follow the same conventions of how to work with them. And so yeah, so like here we choose this beta distribution, and it has two parameters, lambda, or here concretely concentration 1 and concentration 0, and how they defined. So they're defined as TensorFlow variables, TensorFlow variable here, and they have an initial value which is just randomly chosen in this case. So you have to initialize these exactly as we initialized the empirical variables. And there's one subtlety here is I told you earlier that concentrations must not be negative. And in order to make that sure, we have here this soft plus function. And what it does, it takes any given number and makes sure that it's positive. So it applies a transformation that makes it always positive. This way we don't run into trouble here. And now what is this closeness? So when we looked at this here, I said, well, you have to come up with some quantity that describes how close now your initial object of interest, the posterior, is compared to the thing you're replacing it with, this Q. And in Edward, you have several choices. The one we will pick today is KLQP. KL stands for Kalbach-Leibler. And the whole thing is called the Kalbach-Leibler divergence. And this thing measures, it's just a measure for closeness between two probability distributions, here P and Q. So if this thing is 0, then this means they are the same. If it's positive, it means well, it's not the same. And the larger it is, the less similar they are. Okay, so the inference method is called QLQP. And again, follows the same scheme, so latent variables. Here we have to assign p heads to this distribution now that is variational in nature, so this beta distribution. And then we bind this also, the coin flips we bind to the observations, and then we run this. And in this case, we run it for 1,000 iterations. So previously in the Markov chain, we had to define how long the chain is. This is now basically replaced by this n iteration parameter here, 1,000 iterations. Yeah. Yeah, for type of coin, probably not, because this is some sort of categorical information, so this is discrete. We can use it if you have more than one coin, which we will do shortly. Can you say this again? Yes, but we won't learn about this today. So one thing I told you before is that Edward very much places emphasis on composition. So all the things you work with are compositional. So you have these probability distributions. So you have the beta and you plug it into Bernoulli. So the composition here is basically you plug this in and you build this graph. And inference itself in the software is also very compositional. So what you could do is you could run HMC on all the smooth continuous variables, and for the categorical ones you could use MCMC, and you could compose these two inference algorithms to build a new one that is suited to your problem. But this is in practice this is tricky to get right, and what is beyond the scope of today's tutorial. Yes. Yeah. Exactly, it's variational calculus. So it's optimization basically. So like you look at the derivatives, you do stochastic gradient descent, and this is why you can use TensorFlow for this so well, because in TensorFlow, I mean, it was made to do deep learning, and deep learning you have the weights of these layers, or perceptrons, and you want to basically fit them to your observations as well, and you do this with stochastic gradient descent. And all this machinery that is already available in TensorFlow can then also leverage for HMC. And this is why Edward becomes scalable, because as you know, TensorFlow can be used for distributed computing and can be used on graphics cards, which are fundamentally parallel. All right, a little demo of variational inference. Okay, so this is now the variational inference description that we just saw before. So I include 2 lines that are commented at the moment. I will leave them commented. Just to explain a little bit what this strange softmax, not softmax, soft plus thing is. This is a plot of the softmax function. As you can see, for positive values, it is the identity function. So input values match output values. Like a 4 is mapped to a 4. A 2 is mapped to 2 and a bit. But then the closer you get to 0, the more it bends. So like you see, 0 is actually a dramatically positive value, and then negative values are mapped to positive values. Yeah, it's like a really smooth way of making sure that values are always positive. And here it's used to make sure that the random samples that I have here don't mess up my concentrations. You see, so like if this were a negative number, this makes sure that this can't be, so that the concentration is always positive. Okay, let's run KLQP. And this loss that is shown here is the value of this Kullback-Leibler divergence, basically. I mean, no, it's not exactly this, but it's something that has to do with it. But you can think of it as something that the larger it is, the worse, basically, this works. So you want to have a small loss. And let's plot the result. Oh, doesn't work. So here you can see that the red curve, and this is the end result of this method, doesn't show the green curve, which we got all the time now with MCMC. So this method, unfortunately, is not foolproof. You can get into issues. And one of the issues is that this is an optimization now. And it could happen that you are trapped in a local minimum that is not the global minimum. And this apparently happens here. And I can so if you don't know what the real answer is, this could actually fool you into believing that there's much more uncertainty than there truly is. So you have to be wary of this method just not working correctly. But we can fix this here. I think, I don't know if this works with my current values, but when I ran this earlier, it was a simple fix by just changing a little bit the initial values. So if I not say, oh, I have just random values for these concentrations, but if I go a little bit in the vicinity of what my final answer will be, then hopefully, still computing. Yeah, it works. So and what I did was, instead of saying, hey, my initial values that I start with for these concentrations are like super far away from what potentially could be, I went very much in the vicinity of what the final result should be. It's a bit cheating because usually I don't know what the vicinity of my posterior is. But just to show you that this can work in principle is I changed this such that this method actually doesn't fail. So you can see like the answer red curve is now very close to the green one. There's still some variation, so it's not exactly the same, but this has also to do with the fact that well, it's a random stochastic gradient descent optimization method. So there always will be a little bit of variance. All right. Okay, I don't know what just happened. Oh, it went away. Ah, the cable went out. That's back. Yeah, you could run this and look at this and maybe also make this change that I did here. And if you have different values, so like if your exact posterior is different, then you can maybe try to come up with values that give you the right result and not give a wrong answer. And after that, we can actually do our first application of all of that. It is not a simple coin flip. All right. Actually, I don't have any more slides, so now we're constantly in the notebook. So yeah, so the first application that we're going to study is A/B testing or A/B dot 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 testing. So you don't necessarily have two, but maybe more possibilities you want to choose from. So what we're going to do here is we want to say, okay, we have a situation where we have not one coin, but we have a multitude of coins. We have maybe 4 of them. So basically, we have now 4 data sets of coin flips. We have one data set with 50 coin flips, one with 90 coin flips, one with 10 coin flips, and one with 1,000 coin flips. And these are all different coins. They're not the same coin, they're different coins. And if I simulate this, and I have this little model here that draws from that, I get these answers. Actually, I don't like these answers because they're a bit close together. So let me do this again. Well, slightly better. Anyway, so you see that the two values of these 4 coins are all a little bit different. So there's one coin that is very biased towards heads, and the other ones, they're, well, I don't know, semi-biased, but they're all very similar. And now the challenge of A/B testing is to figure out which is the best coin. And the best coin in this sense is the coin that is most biased towards heads. So where could this be useful? Well, for instance, if you run an online store, or if you're like putting ads on a web page, you want clicks, yeah. And the higher the probability of an ad working, that means leading to a conversion or leading to a click, the better. So you count clicks, you count conversions, and these are basically then your coin flip results. So your head would be a conversion, if tail would be no conversion. And then the challenge is to figure out if you have, let's say, 4 different ads with different motives maybe, but they're all advertising the same product, then maybe you want to figure out which is the best ad, which one should be shown to people. So you want to infer the fairness or the efficiency or the success probability of this ad, or the conversion rate. And here, if you think of this in terms of ads, so this one would have a good conversion rate, actually all tremendously good. You will not find good ads that well, but you can think of this as like some sort of like simplified version of this problem. And you see that this ad here was very good, and these were not so good, but also still good. So to visualize this, so what I did here is I specified that I want to have a beta distribution, and I gave it the parameters 10 and 5. If you plot this, you will get this curve here. So that means like the coins that I generate here for these observations, most likely their fairness will be in this region here. And you see the 4 coins that I pick, like the blue, green, red, and purple one, they are in this region indeed. And this is the one that is best, and these other ones are not so good. And so the training data set looks like this. So the first one, I think, had 50 flips, 90, 10, 1,000. So that means like for the last one, which is extremely good, we have for some reason 1,000 samples. So we have a lot of data here to work with. This one has very little data. This one has well, the same amount roughly of data than previously in the coin flip example, and the other one has half as much. So very different numbers here, and you can see what the data is. And how do we find now, how do we study this problem? So the first thing that we will do is we will treat this completely independently. So we say like, okay, these coins have nothing to do with each other. We're just basically building a model that now in parallel solves the inference problems for all these 4 coins, but not really using any crosstalk between these solutions. So that means we're doing inference for the first, the second, the third, the fourth, coin fairness, and then we look what the what the result will be, but we will not use any structure that uses the fact that these are all coin flips that are standing for, let's say, the ads for the same product or so. Yeah. And if I do that, this will take a while. So as you can see here, what I do is I define p heads as a list. Yeah, so like it's a list of betas now, and they're all the same. So I have 4 coins, so this is the number 4. And I'm just iterating through this, and I'm defining 4 beta distributions, all the same. So the same prior for all 4 coins. And then I have the C also defined as a list. There's 4 different Bernoullis, and I'm just feeding in the corresponding prior for this coin. But they're all the same, so I could actually use the same one if I wanted. And the backward model, because I'm using HMC in this case, is again an empirical distribution. So this again is just a placeholder now for the chain. And it seems to take a lot of time here. I'm not really sure why. Oh no, it's faster now. But it will take a few minutes. And hopefully it does not run too slowly on your computers. But as you can see, there's a little bit of subtlety here. So someone made me add actually a list that wraps this here. So I should probably do that too. So if it doesn't work, add list here. So what this does here is basically it just builds a dictionary that binds these variables. Like the first p heads is bound to the first 2 p heads, the second to the second, and so on and so forth, and the same for the data. Now this is just a way to make this quicker here using zip and the dictionary constructor. And yeah, you could run this now if you wanted. We probably should have. And now I have to just wait. Are there any questions? Bless you. What is the question? I don't. Yes, yeah. The probability is described by the posterior itself. So like for each possible value that the fairness could have, the posterior gives you the relative likelihood of this value. Yeah, you don't, and you don't want to, and that's the whole point here. So you don't really get a fixed answer. You don't really get, oh, this was the fairness of the coin. You get a spectrum of possibilities, and you get likelihoods attached to each possible value. And this then, again, you can use for further study. So you don't get a definite answer. And this is because there's still uncertainty. If there was no uncertainty because you have infinitely many coin flips, yeah. Okay, it's done. All right, so this is a bit messy now. This is because there are 4 chains running together now. So, but you can probably see that I have 4 straight lines in there. So these are the true values. And what we want to have is that the chains of these 4 coins somehow evolve around these lines. You can see the purple one, which is in the top here, it achieves this. The green one is somewhere here. Yeah, well, it has a lot of spread. The red one is all over the place. And if you remember, the red one is the third color, and the third coin here has only 10 examples. And that means like there's a lot of variability, and this is captured in this picture very well because this chain is all over the place. So there's a lot of uncertainty still. Whereas for the purple one, it's very narrow. You see, because there's 1,000 coin flips that we're looking at, it's very close to the true value already. But again, the true value we never really get to see in these experiments. So if you look at the lag and the, I already executed this. Let's do this again quickly. Yeah. So the lag here, so this was this quality measure for these traces, shows you that the trace of the purple coin is the best one. The red one is actually quite bad. And the other ones are also not too good. So like this has to do with the fact that I chose values here for HMC that are good for the purple coin, but not really that good for the other coins. So actually you want to somehow have a value that is good for all coins, and you have to tinker around with this. But given that this takes so long to evaluate, here it took 230 seconds, this is something for a rainy afternoon or something in this case. So I won't do this now, but in principle, you would have to do that. And this is the posterior that we get. The posterior now is 4-fold because we're 4 coins, so we had 4 distributions now. We got the distribution, so we don't get a joint distribution, or we actually get a joint distribution of all 4 coin fairnesses, but they're all independent. So that means we can plot them individually and don't have to like make a 4-dimensional plot of this. So the purple coin here were very good. It's a little bit off. I don't know really why. The red coin, well, it certainly is covered in the right region, but there's still a lot of uncertainty. Blue is quite good. Green is not so good. And now the question that we actually want to address is, so if you had to decide, so if these were ads and we wanted to decide which of these now is the best ad given the data that we saw, while looking at these plots, we already know what the answer is. It's probably the purple one, because there's a lot of certainty here that this is a high value. The red one could also be good, but we don't know really. So we would like preferably look at this one of our final answer for the ad that we want to choose in the future. And we probably want to abandon those here because they're not really good. And there's a quantity that helps you to make this sort of decision, not really by looking at these charts here, but looking at a different kind of chart. And the value we're looking at here is the so-called lift. So how do you compute this lift, or what is this lift actually? So what you do there is you compare each value of the chain with a different value from a different chain. So like you compare, like, let's say a value of the green chain with the value of the purple chain, and you do that here. So here's the definition of how that works. So the samples of one chain are subtracted from the samples from another chain and then divided by the samples of the same chain. And you compare that with 1. So what that means is you're looking at which gives the better result, which is better. And you do that not for a single value, you do it for all values. So what you get is you get an aggregation, you get an average basically over all these chain values, and this gives you a probability. So you can say, what can I say? Can I say that coin 1 is the green coin, is now better than the coin number 0? And if you just ask this question, is it at least as, if not better than, then you have to go here in this graph and look at 0. And to get an answer in terms of probability, you can say, this chart tells you with 75% probability, you can say now that coin 1 is at least as good, if not better than coin 0. And then you can go to the left or the right, and what that means is you say, okay, is it maybe 25% or better than coin number 0, the coin number 1? And you can see here that we cannot really say that. We can say like always with 0% probability this is actually the case. So what's more likely is that it's somewhat better, but not really that much better. And you can see that here too, and it's actually the truth. So like we're comparing here blue with green. Blue and green were almost on top of each other. So these were really, really similar. So we cannot say really much, but the spread of this lift probability plot here tells you that also we're not really certain about all of this. If this was a really clear-cut decision, if you had, like, let's say, I don't know, 10,000 samples from blue and 10,000 samples from green, what you would observe is that this S shape here, famous S shape, would be very, very narrow. Yeah, it would almost be like a step function. And you can do that now with all possible coins pairs. So like you can compare coin 2 with coin 0. You can compare coin 3 with coin 0. You can compare coin 2 with coin 1 and so on. 3 with 1, 3 with 2. So I have all possibilities now. And we know that coin 3 is the best. Just looking from this other plot here, how would you see this here? So if you look at, is coin 3 better than coin 1? We can say this with almost 100% probability. Yeah. Is it at least as good, if not better? Yes, absolutely, almost 100%. Is it more than 25% better? Probably not, but with high likelihood it's actually better, let's say 10% better with, let's say 75% probability. So we actually quite clear, and you can see that we're quite clear here is that this shape is very, I mean the slope here is very high. Can we say that coin 3 is better than coin 2? Coin 2 was the green one, I think, yeah. And there's a long tail, so that means that we cannot, I mean, it could even be that given the data that we saw, it could even be that coin 3 is much, much better than coin 2. And we cannot really fix this because so coin 2 was the one with, I think, only 10 examples, and and this means that the plot here was very, very wide, so there was a lot of remaining uncertainty, and this is captured here in this plot due to the fact that this lift function or this lift probability is also very, very widely spread, and there's this long tail here. So you cannot really say how much better it is, but you have a good intuition here that it is much, much better. All right. Yes. This is a good question. So one case is where the data set is too large, or the model is too complicated for the size of the data set. The reason is that MCMC is a fundamentally sequential operation. So like you have one chain element, you compute the next one from the previous one. So you have to have all previous ones to do the next step. And the next step is just a single application of a single function. And you cannot really parallelize over that. You can maybe run different chains and then aggregate over different chains, but you're not really benefiting from these two different chains. So like the decisions made in one chain cannot really inform the decision made in the other chain. So they're independent of each other. And generally actually should run more than one chain to get a better feeling about how good the algorithm is. So for instance, or how good the inference works. So if you have different chains and they all do very, very different things, then you can be sure that something weird is going on. You should probably look into either your model or your inference and treat this a lot probably to get it right. So MCMC is sequential, and that means it doesn't really work that well for a lot of data. So what variational inference allows you to do is, because it substitutes this this Markov chain with this optimization problem, is it allows you to do the so-called data parallelism. So that means like since it uses optimization as optimization is part, or is like the fundamental part of this method, you can spread out the data over cluster, for instance, and run this on different nodes and aggregate of the results, and it will be better parallelizable than MCMC ever could be. You have problems, of course, with the method itself. So we have seen that sometimes it can get trapped in local minima. They're not really corresponding to the true solution. But this is, I guess, something you have to live with in some cases. Also, variational inference tends to be faster than MCMC, so especially HMC. It took now 250 seconds. So I think if you had done this with variational inference, this could have been done in like 10 seconds, but I didn't want to do that because HMC is used in the next thing and it just leads to that, so I didn't want to substitute that. But even though variational inference is, or can be worse, results can be worse, especially if your variational probability distribution that you choose, the Q, is not the right one or is not capturing the essence of your problem, it helps you to come to quick solution and you can iterate quicker. So you remember what you want to iterate, you want to go through this loop over and over again. So if you even come up with something crappy that works in the very beginning for the first step or so, that helps you revise your strategy and your modeling approach more frequently, you can do that maybe with variational inference better because you get a timely answer. You don't have to wait 300 seconds for your answer and like have these copy breaks all the time. And that makes it nicer to work with. Yeah, I tried. It's difficult because I mean we can look at the definition of the lag, but so it's TensorFlow code, so it's a bit dense. So like basically what we're doing is we're looking at the samples that are in the chain. So like all the elements of the chain. And first what we're computing is the mean, and then we're computing the variance. So these are these two lines. So the mean is just the average, and the variance is what is the average of the difference of every value compared to the average. So I'm looking here at the square of x, so x is the sample, minus the mean that I got on the previous line, and then I square this, and then I compute the mean of that. So this is the variance. And I don't remember why I had to do this cast here. I don't remember. Anyway, so like the next step is actually a tricky one. I said what you do is you, for each possible shift that you can do on this chain. So like you can think of, you compare the chain to itself, but you can also compare it to itself moved by one element. So like you compare the first element in the chain to the second element of the chain, the second to the third to the fourth, and so on. Or you can do this with an offset of 2, the first to the third and the second to the fourth, and so on. Or with a higher offset. And this iterates over all possible offsets and computes this reduced sum here. And if the offset is 0, this will just correspond to the variance as it is defined here. If the offset is larger than 0, this is what is called the correlation. And then in the end, we divide this by the variance so that the thing is normalized to 1. So it can be larger than 1. And that's it. So this thing actually measures how much information is in this chain. So if this is good, or if the values are small, then it means there's not much correlation. So that means there's not much repetition in this chain. And this is good because this means we can use more samples from it. If there was a lot of repetition, then that means that the value of the lag would be larger. And what we could do then is there are several techniques to work around this. We could thin the chain, so that means we just exclude every 5th element or so, or every 2nd or 3rd, and we have to play around with that. So you throw away things because you know there's repetition in there. This brings down the correlation. And the other techniques. I don't remember where we were. Okay. So we studied lift. Was the lift at all intuitive? I know it's a bit difficult because when the value 0 is easy to grasp, but because this is the question of, is it at least as good, if not better? But if you then pick a number here, 25, then it means like, is it at least as good plus 25 than the other? Yeah, so like it's a bit hard to understand. Anyway, so now I don't know if there's time for that. maybe we want to actually move. Yeah, I think we have to move on. But just for the adventurers, or if you want to do this at home, you can certainly do that. So in this part here that I included a hierarchical model. So what that means is you compose or you make your model more complex by composing it. So that means what we did before above was we had these 4 coins, and what we did was we had different models, independent models for all of these coins. We had different priors for all of these 4 coins. And with this hierarchical approach, what you do is you assume that there is something that connects these 4 coins. So if it was, let's say, different slogans for the same product, like if it's very similar ads, and they're made by the same ad company and or agency, and there's some underlying theme, or the product is even the same, that's also something that connects them. You can assume that there is some intrinsic value for the success of this campaign. Yeah? And you can model this. You can actually say that, hey, these beta distributions that I put as prior, actually their parameters, they should also come from the same distribution, because they would somehow be connected. And that means that, like, learning about one coin and its fairness, or one ad and its success, will also teach you about the fairness of the other coin or the other ad. And there's some information exchange. So one problem helps solving the other problem. And this is why these hierarchical models are useful. So basically what I do is I put a prior on the prior. So I introduce a new layer, a higher layer in this scheme, and make it deeper. And this increases the complexity and also makes inference harder, but it also usually leads to better results. And this takes 20 minutes to evaluate. I don't think we have the time for that, so we'll skip it now, but please try it at home if you can. It's quite interesting. All right. The next example I want to talk about is linear regression. So in linear regression, let me just execute this so that we get a picture of that. In linear regression, what you do is you assume, this is your prior assumption that you put in there, that some relationship can be explained by a straight line. So here, what I have are 2 point clouds, a blue cloud and a red cloud. And the blue clouds are actually the data points, and the red I will hold away, and I will say these are my test data points. So these will be used later to evaluate the performance of the model. So I'm not using them for inference. I'm also only using the blue points. But you can see, like, if you squint your eyes, you can see maybe there is like a line that connects them, or somewhat, in some fashion, gets close to all these points. Maybe not go through all of these points, but maybe some. And the question now, what is the best line to fit to these points? And usually when you solve this problem, you use maybe a package like scikit-learn or so, and it minimizes basically the error when you make this. So like when you put this line in there. So it basically measures what is the difference between the line that you put and the points. And then it sums over this. And this is basically some sort of like error function or some sort of loss function that needs to be minimized. Some penalty, basically. You wanna make this as small as possible. But in the Bayesian world, you don't look for the single line that is the best solution. You look for how much actually can we say that there is a line that fits those. Like, what is the remaining uncertainty that we have if you fit a single line through this? So we don't get one line, we get many lines. And we get a probability distribution over lines. So how do we do this here in Edward? So let's look at the forward model. So we have a placeholder value, and this is a new thing that we haven't seen before. I need some way to store these training examples that I have, these blue points. But I don't want to store them in the graph itself. That would not be very efficient. Not store in the TensorFlow graph, that would not be very efficient. So what I do is I just say, hey, at some point I will need n1 times d, this dimension of the problem. In this case it's 1 because it's a one-dimensional x value here. I need a thing, an array that has size n1 times d later at some point. And then what is the description of a line? Well, what you do is you basically start at 0, 0. Then let's say you go up, and then from there you go on a slope, and then you connect basically points. So the parameters that I have here, instead of like the bias of the coins, is things that I want to infer are now the weight. So this is basically something that describes the slope of the line, and the intercept. The intercept is basically how much away do I go from the origin on the y-axis. And then I need something that introduces randomness here, because so far everything is deterministic. You give me an x, I multiply this by the weights, add the intercept, I get a point. So I want randomness here. I want to describe the thing that makes these points not be perfectly sitting on a line. I want some spread around the line. So what I do is I pose a new distribution here, pose a new distribution which is called the normal distribution. This looks like a bell curve, and it's centered around some value. This is the location, log here. And as you can see, as location, I pick the equation of the line. I pick x times slope times weight plus intercept. So this is a point on the line. And the Gaussian, or the normal distribution will be sitting with its mass at this point, but it will have some spread around this, and this is the scale value. And the larger the scale, the larger the jitter, the larger the noise around this location. And you can see I initialize this here with ones, and then I multiply this with 0.0. So this will be small jitter, small noise. And then I need a backward model, and I'm using HMC again, so that means I need two empirical distribution, two placeholder for two parameters that I'm going to infer, the weight and the intercept. And then I'm running this, so I have to tell Edward a little bit more here. I have two parameters, so weights and intercept. Weight goes to Q weights, intercept goes to Q intercept. And then the data, well, I have X values and I have Y values. So I have to feed both. And this is where this placeholder comes in. You see, I define Y in terms of X. And X is a placeholder, so here I bind this placeholder to my X values. I bind the Y values to the Y values. And then I run the inference. And let's look how well that works. And I think this takes a little bit to evaluate. It's funny, actually, the plotting now of these curves takes longer than HMC does. So what I'm doing here, this is a bit dense, the code, but basically I'm plotting the initial data, so these blue dots, this is the training data, then I plot the training data, so these are the things that I want to predict potentially, and then I'm plotting a few possibilities of what this model now predicts. So you know, like previously we had this posterior distribution. Now I cannot really plot this anymore. I cannot really plot this probability distribution in the space in which I draw these dots anymore. But I can do an approximation of that by basically drawing from this posterior and plotting many lines on top of each other. And you can see what the result is here. So this really wide black line is actually not a single line, it's many lines that are sitting on top of each other. They all have some alpha, some transparency, so they're only 10% opaque, and they all have the color black. So that means like their opacities add up, and if it's really black, that means there are many curves on top of each other. But the lighter this gets, the less, or the fewer curves actually are there. And you can see that the model is very certain in the middle here, but it comes to more uncertain you go away from the data it has seen. So if you go further out, this will spread out and you will get like all possible choices because the model doesn't know at all what's going on there. It hasn't seen any data there. And so this works. However, to my feeling, to my understanding, it's too certain of what's going on. You see that these red dots here that are in the in the test data set, you see that almost half of them are not really on this curve. Yeah, like if I made a prediction for this x value here, I would get this value more or less, or like a little spread around that. But the true value for this test data set is here. So there's a huge gap. There's a huge error. And somehow my posterior actually should encapsulate this. It should not give me the false impression that this bundle of lines that I have here now is always applicable, always gives me accurate predictions. It should actually encapsulate, should describe that my posterior, my results will have some spread, will have some remaining uncertainty. And the remaining uncertainty is just too small. So how can we fix this? So we just play around. So what if we just choose more noise? Remember that like in the beginning I had said that here you choose this normal distribution, which defines where the line sits as location, and then there's the scale which determines the jitter around this location. So what if we pick a larger value? So before, up here, we said 0.01. So it is a very small value. What if we choose 100 times more? Let's do that. And this will take a moment. Yeah, don't get scared by these numbers, they go away. Yes. It's criticizing the results so that you can move on or make changes. It's just convention, I guess. You criticize. So when you do science, what you always have to do yourself is you have to criticize yourself. You always have to question your answers. That's the only way you can move forward. You cannot just say, hey, oh, I'm okay with that. Why not? No, you have to always try to prove yourself wrong. If you can't, then maybe you're on a good track, but it doesn't always mean that you actually are right. But if you can prove yourself wrong, you should make an effort to do that. And criticism is just about that. So you're just doing some things that just give you more confidence that what you're doing actually is correct. All right, so Inference has completed in 50 seconds. It took this time, but criticism means plotting in this case, and we're still waiting for these plots to appear. And the reason this takes so long is that I'm not plotting one line, I'm plotting like, I don't know, a few hundred. Yeah, please. I would like to use it more. Currently we don't. The thing is, I'm using this tutorial also like to familiarize myself more with Edward. So I'm actually using Stan, if I can. So it's a different software, but Stan is not as parallelism friendly as Edward is or could be. And Edward is still a very young project, so I wouldn't really put it into production yet, I would say. But it's a good way to do research and to get more confident in these methods. And it's also always looking out for more help. So if you want to contribute to Edward, I guess the authors would be very, very glad. So, yeah. Yeah, yeah. That would bit derail now. We could maybe, yeah. So like one thing we could, for instance, work in a Bayesian way as well, and this is something we were interested professionally, is recommendation systems. So if you want to make recommendations to somebody, if you had only a point estimate, so let's say Netflix, yeah, and we will look at Netflix if there's time. I don't, there will be actually, so maybe we postpone that. In Netflix problem is you have 5-star ratings and you want to infer what possible rating could be for a person that hasn't seen or rated this one particular movie, or all other movies that this person hasn't seen. So like you want to infer missing values basically. So you have tons of evidence because people have clicked a star after watching a show or a movie. And then you want to infer the missing stars, so those that haven't been rated yet. And this is a hard problem. And usually what people do is they come then up with a point estimate. That means like they give a single value of what the rating should be. So they predict a single value for a rating, basically, like 5 stars or something. But then they don't tell you what the certainty is of this result. It could be like 5 stars, but the uncertainty is 5 stars. So what does that mean? Or can you even make then a predict, or can you even recommend this then to somebody? So like if somebody, if the model though has this confidence built in, or like has the means, gives the means to evaluate this confidence, then you can also make more informed decisions. So maybe if the confidence is very low, like confidence of, I don't know, less than, I don't know, half a star or something, then you probably don't want to make this recommendation. So this is something you can think of. Anyway, so the plot has finally appeared, and it appears that well, this captures uncertainty more than it did before, but I would say too much of it. So you can see the lines are almost like all over the place now, and you can actually now differentiate different lines that are there. So I'd say that this was a little bit too much noise, and one thing that I would like to do is now that we look into an advanced model that, you know, like we picked this parameter by hand. We said, oh, we have this prior intuition maybe of what the noise should be. But why would we? We can also say, hey, give it a range or give it a prior. So, and we know what that means now. It means we make the scale, like this noise level, a parameter itself. And that means we have to a parameter you want to infer. That means that we have to pick a probability distribution for it, a model. And here's a possible choice. So this is this inverse gamma function. So never mind what that is. It has nice properties. The first one is it's always positive. And this is what we need here, because a noise level always is positive. And it has 2 parameters, a concentration and its rate. And you can see here 3 plots with 3 different values of these parameters. So for the red, well, it's the blue one. So the blue one is fairly narrow, and then it has this long tail. Yeah? So like it rises rapidly, and then has this peak and goes slowly to 0. And then these other ones here, and this was for large concentration. So like concentration literally is concentration. You make it more concentrated. And then for a smaller concentration, this peak now wanders to the right, so to higher noise levels. And also distribution becomes wider, broader. And for concentration level 1, which is the red curve, is really like smeared out. And what I also included here is the 2 noise level, which we usually don't know, which I actually don't know here. Yeah, so like I drawn this because I simulated data myself, but normally you don't know that. So you just include this additional distribution here. So like here it is, the variance, the noise level, is now this gamma distribution. I picked the blue curve, so this one. And otherwise the model hasn't changed. So I only do one thing, and this is, I don't know, this is what statisticians do. Like if they have inverse gamma, they usually take then the square root of it, because this describes the variance, and this describes the standard error, and they're related by squares. So that means if you have the variance, you have to square root it. And this is done here with TensorFlow.square root. And yeah, so like then let's run this. So the backmod model now includes 3 empirical distributions, not only weights in the intercept, but also this variance parameter now. And the chain will run now. Again, HMC, and we have here this additional dictionary key value pair of var and qvar. And let me just queue this up here because I think this takes a while. Are there any questions maybe that I could answer? Yes. This here. So the top half are more like research papers. Like the first one is a paper of this group of researchers that works on Edward from Columbia University. It's fairly accessible, has a lot of code examples. So it's called Edward, a library for probabilistic modeling, inference, and criticism. So if you see such an address here, archive 1610, blah, 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 just Google this thing. So archive is a repository for preprint papers. What that means is like any researcher uploads their paper there, and it will render it as PDF, and everybody can download it. That means that if you go to the final journal where this paper is published, usually there is a paywall, and archive doesn't have any paywalls. So this is nice. The second one, Deep and Hierarchical Implicit Models, is a more technical, more advanced model. I can highly recommend it because it also points towards new improvements in Edward that are just exceptionally interesting and open up possibilities for really interesting modeling approaches. Then Deep Probabilistic Programming explains a bit more the rationale behind modeling in Edward. And then if you want to learn about Variational Inference, there's a very nice NIPS tutorial by the head of this department, of the head of this group. And I don't know, I think there should even be a video so you can watch this. And even if you Google on YouTube for Edward, I think there are like 1 or 2 talks by Dustin Tran about Edward that you can watch, and they're actually watchable. They're good. And where you can get help, well, Edward itself has a GitHub channel, and I can recommend going there. You find me there as well, because I also ask questions and I also don't know everything there. So very helpful community. And there's also a community forum. So this is more like if you have shorter questions, this is like, hey, I have this long model and it doesn't work, please help me. Or there is a bug and you want to file a bug report or something, you can go there too. And of course, Edward is open source. You can also go to GitHub, check it out, and even hack on it if you wanted to. Oh, that's finished. Okay, so so it ran for 91 seconds, and this is understandable because the model is more complicated. So we included this higher level there, this prior on a prior, and also we have 3 chains now that we run currently, or like 3-dimensional chain. And let's see what the model infers for the variance for this noise level. You see that here's the plot of this. So if this is the chain that is only concerned with the noise level. And you can see this is the histogram, and the true value of the noise sits here. So this is this vertical line. Unfortunately, the colors are too similar, but you can see that like this is this value here, and it's almost concentrated around this region. Which is good, I guess. So the model actually finds out the noise level. And then if you look at the weights, you can do similar plots. So what is the distribution of the weights? This looks bad, but then you realize, oh, the x-axis is actually 1.5, 1.75. So it's not too far away from the true value. And then the intercept, so this is the y-axis distance of this line. Also, well, I mean, it gets close there, but maybe there's some difference. And so if you plot then this distribution of possible lines here, you get this picture. And you can see it looks a little bit similar to what we've seen before here, but I think it captures the uncertainty better than before. And this is just because we made the uncertainty, so the noise level of this problem part of the inference. So whenever you don't know anything, just put a prior on it. This is the message of this little exercise here. Where putting a prior on it means you define a statistical model, a distribution of this particular parameter. In this case, it was the noise. And we used this inverse gamma distribution. This is hard to answer. Like from experience, I would say I have no Greek clue. Sometimes like I feel this should be really easy, and then it takes ages, and I don't know why. I don't know. I haven't developed a good intuition for it yet. But this is certainly something you want to consider. Absolutely, yeah. But this is why you start with simple models. You start with simple things. Hope that they explain the story sufficiently, and if they don't, or if you want to capture more fine-grained features or structure in your data, then you have to make it more complicated, which will then increase the inference time. All right, this part we're gonna skip. Has everybody arrived at this point here? So we don't have that much time left, maybe 9 minutes. So I said in the beginning that maybe you do this here actually. So this is actually, how much time does this need? A couple of minutes, that's good. In the beginning I said it uses state-of-the-art techniques of deep learning, or the deep learning community, and uses TensorFlow. And so where's deep learning here, please? Can you show me deep learning? Let's do this. So we studied linear regression now, and we can also study nonlinear regression. And usually when you study nonlinear regression, you have to think about, which function do I pick? What should my target function be? What should I fit? Like, should I pick a polynomial, like a higher order thing, not a line, but something that involves x squared, x cubed, and so on, with more parameters? Or what do I pick? What model do I pick? And deep learning, well, solves this problem quite elegantly, because you don't really have to think about this other than the structure of the neural net. So I'm using data here that comes from a very weird function that I just cocked up. So it is x times some weights that I draw, and then I square it, and then I put it in a sine, this a sinusoidal oscillatory function, and then I add an intercept. So this is the target function. This is the thing I don't know. So this is basically some sort of like underlying truth of my points that I see, my data that I get, but I never get to see this. So this is the thing I want to fit, but I don't know it. And then I build my data set. So I build x and y values. And this I do here. So I have training data set, and I have a testing data set, and I can plot this. So this is how it looks like. I have this M shape. What you can see there are like things that happen here. And the reason is there's not much going on is because the x-axis is drawn, or the values on the x-axis are drawn normally. That means like the bulk is in the middle for 0, and there's not much going on outside. And then you have this oscillatory structure here. So how would we fit this? We certainly don't want to fit this with a line, because where would we put a line? Would we put it like this, or like this? We couldn't maybe stepwise. We can like, I don't know, we could restrict our data set, let's say, to the region between -1 and 0, and claim like, oh, there's a linear dependency here. But then you look outside this region and you see, oh, wait, it goes around here, and there's a different line. You can maybe think of piecewise linear, like here, one line, then there another, here another, there another. And this would probably work, but a lot of engineering, and we are lazy. So why not a neural net? And since this is based on TensorFlow, we can just use now TensorFlow primitives and TensorFlow functions here to define a neural network. And I will define a neural network with 2 layers. And 2 layers means we have in total 4 different kinds of parameters. We have weights, and we have biases or intercepts. And there's this nonlinearity here. This is tan h, tangents hyperbolicus. And we have some matrix multiplication, and then there's some madness going on for reshaping this. So basically, each layer is fed from a previous layer. We have 2 layers in total. There's not much going on here. And we produce a single value, a single y value. And we can specify the dimension of the layer, so how many variables I have hidden in these layers. And we can also then, and this is the Bayesian aspect of this, which is not usually done when you use TensorFlow, you specify priors now for these weights and bias terms that you have in these layers. So here W0, W1, B0, B1 are all now distributed according to normal distributions. And the challenge here is to do inference on the parameters of the neural net. And how do we use this neural net now? So we again use this normal to capture the fact that we see here jitter. So this is not perfectly like zigzag. This is there's some randomness in here. There's some noise. And again, we use this normal. And the location will be based on the output of the neural net. So like neural net, the input is an x. these weights that we initialized, or that where we said, okay, these are normally distributed. The prior assumption is they're normal distributed, which just means that in this case they will have some value, but we don't know what the value is, and we assume some spread. And the B's will also be normally distributed, and then out comes basically position, but this is then fed into normal, and the normal will add then some noise level, and here we pick a constant noise level, just 0.1, not to not make it too complicated. And then for the inference, I will use variational inference, and this is then, since time is running out, the only example where you see variational inference really in all its glory and why it's useful. We define now a substitute model, which says, okay, for each of these variables, I define these Q functions, and they are just normal distributions, and they have location to scale, and where the location is and what the scale is, so the noise level of these normals, I don't know. So I initialize them with a random value, but I give them the right dimensions, and I mark them as variables. So that means that Edward can realize that these should change and can change. So it will try to optimize over them. And this defines our backward model. So this defines the substitute posterior that we are gonna fit. So like basically the location and the scale of each of these normals will be fit such that this backward model, as best as it can, fits the real posterior that we otherwise wouldn't get. Because I think if you try to run HMC on this, this will just be nuts. I mean, this will take too long. So, and this inference method will probably take 2 minutes or so. And we're curious what happens now. Last time I ran this, results were mixed, but let's see how it is now. Yes. Yeah, I'm closing. Yes. Would it help to put the other link on this pamphlet? I just put it. Let's just put it quickly, as if people then. Yeah, this one. Okay. Okay. Okay, it's almost done. Oh, has to plot lines later. Also, maybe I leave it on. Oh, they're done. Yeah, I think we're out of time here. So you're invited, of course, to stay and see the result of this, which will be hopefully quite amazing. Otherwise, thank you very much for coming. It was a pleasure to give this here today. It was my first tutorial. Oh, it's done. Yeah, so there we go. It's not perfect, but you see it captures the structure at some degree. And I think if you ran this for longer, so if you increase the number of iterations here, you would see that it better and better approximates the target function. Thank you very much. Let me just get the audio. Hello.